Hey there, focused learners, and welcome to The Explainer. Today, we're taking a really fascinating look at something that might completely change how you see numbers. We aren't just doing regular math today. No way. We're going to treat our source material like a secret code book. Because honestly, math is full of hidden patterns just waiting to be cracked. So let's get into it.
Okay, let's dive into this. Picture this massive number, 32,768. If you saw this on a test and were asked to find its cube root without a calculator, you'd probably panic, right? I would. But don't worry. By the end of this explainer, I'm going to teach you a mental math magic trick that lets you solve this in literally seconds just by looking at it. Here's a quick look at our agenda. 1. The rules of perfect squares. 2. Unlocking prime factorization. 3. Visualizing mathematical patterns. 4. Entering the third dimension. And finally, number 5. That ultimate cube root shortcut I promised you. Section 1. The rules of perfect squares. We're discovering the hidden identities of numbers. Now, what's really interesting about this is how you can spot an imposter almost instantly. Think of a perfect square as this exclusive VIP club, right? Not just any number can get in. If you see a number like 2032 or 1027, you can kick them right out of the club without doing any complex math. Why? Because they end in a 2 and a 7. A true perfect square can only ever end in 0, 1, 4, 5, 6, or 9. It's a totally ironclad rule built right into how numbers multiply. And the neat tricks for squares? They definitely don't stop there. Let's say you already know that 125 squared is 15,625, but you suddenly need to figure out 126 squared. You absolutely do not need to do that tedious long multiplication. There's this incredibly elegant little rule. Consecutive squares always differ by 2 times the first number plus 1. It's just 2n plus 1. So to get 126 squared, you take your previous answer, add 2 times 125, and add 1. Boom, 15,876. It is so simple and saves you so much time.
Which brings us to this very specific, kind of dramatic number, 198. Using that exact same 2n logic, if someone asks you how many non-square numbers are squeezed perfectly between 99 squared and 100 squared, you don't have to guess. 2 times 99 is exactly 198. Bam! That's 198 distinct numbers just chilling between those two perfect squares. It's a flawless example of the hidden order inside these sequences.
Moving on to Section 2, Unlocking Prime Factorization, the master key to mathematical building blocks. So if rules and patterns are our blueprints, prime numbers are the literal Lego bricks we use to build every other number. It's our trusty toolkit. Now, for a number to be a perfect square, its prime factorization has to be completely, perfectly balanced. This means every single prime factor making up that number must have an even exponent, pairs of 2s, pairs of 3s, pairs of 7s. If even a single prime factor is the odd one out, the whole number fails to be a perfect square.
Let's put on our codebreaker hats for a second and look at the number 9408. If we break it down into primes, we find it has 6 2s, 2 7s, but only one lonely 3. It's completely out of balance. So what do? We fix it. By multiplying 9408 by just one more 3, we pair up that lonely 3. The new number becomes 28224, which instantly completes our puzzle to form the perfect square of 168. We literally built a perfect square just by spotting that one missing piece.
Let's move to Section 3, Visualizing Mathematical Patterns, and see how this builds into seeing the true beauty in the math.
Because, math isn't just about rigid rules. It's full of beautifully repeating patterns. Just take a look at this progression. 1 squared plus 2 squared plus 2 squared equals 3 squared. Okay, pretty neat. Then, 2 squared plus 3 squared plus 6 squared equals 7 squared. Wait, are you seeing it? Let's jump to the third line. 4 squared plus 5 squared plus 20 squared equals 21 squared. Can you spot the delightful, hidden relationship connecting all these numbers together?
And this brilliantly illustrates the pattern rule. If you multiply the bases of the first two terms, like the 4 times the 5, you get the base of the third term, which is 20. And the answer on the right side of the equation is always just exactly one more than that product, giving us 21 squared. It's this elegant Pythagorean-style identity trick that solves the entire pattern without you having to calculate a single giant sum. How cool is that?
Let's visualize this with a little puzzle from our source. Imagine a structured grid, 9 big squares in a row and 9 big squares in a column. Inside every single one of those, there are 25 tiny little blocks. If we want to find the total, we just multiply 9 by 9 by 25, which gives us exactly 2,025 tiny squares. And tying it back to our toolkit,
2025 elegantly factors out to 3 to the power of 4 times 5 squared. Even exponents across the board, which perfectly proves our rule. 2025 is totally a perfect square.
All right, Section 4, entering the third dimension. Time to level up to perfect cubes. We are officially stepping out of flat 2D squares and expanding into the 3D world of perfect cubes, where the rules get a little bit wilder, but honestly just as fascinating. First things first, we need to cheerfully bust a major myth. Remember how perfect squares absolutely cannot end in an 8? Well, a lot of people think cubes follow the same rule, but they absolutely do not. Cubes are perfectly happy ending in an 8. 2 cubed is exactly 8, and 12 cubed, that's 1728. So yeah, they totally can. If you see an 8 at the end of a massive number, don't immediately write it off as a fake cube.
It's also super helpful to clarify the physical boundaries of these 3D numbers. If you take any 2-digit base number, its cube will always fall into a very predictable size range. The absolutely smallest 2-digit number is 10, and 10 cubed is 1,000, so 4 digits. The absolute largest 2-digit number is 99, and 99 cubed is 970,299, which is 6 digits. This basically guarantees that a 2-digit cube will never, ever have 3 digits, and it's certainly never going to have 7 digits. It's a fantastic little boundary check.
And finally, Section 5, the cube root shortcut, the ultimate mental math hack. This is the exact moment we've been building up to. It's time to solve that terrifyingly huge problem from the start of our explainer. So the crucial point is, finding a huge cube root mentally really just comes down to 2 incredibly simple steps. Step 1 is range. You just find which tens cubes your number sits between to instantly decode the tens digit. Step 2 is the units digit rule. The very last digit of a perfect cube perfectly matches a specific base end. For example, bases ending in 1 yield cubes ending in 1. Bases ending in 2 yield cubes ending in 8, and so on. It's literally a 1-to-1 secret code.
Let's rapid fire through some examples to show you just how shockingly fast this is. 1331. It sits between 10 cubed and 20 cubed, so the first digit is 1. It ends in a 1, so the last digit is 1. Boom, the root is 11. Next up, 4913. Between 10 and 20 cubed. It ends in 3, and the code says bases ending in 7 yield cubes ending in 3. Root is 17. What about 12167? It's between 20 and 30 cubed. Ends in 7, which codes to a base of 3. The root is 23. See? No tedious factorization required whatsoever. And now for the grand finale, our massive friend from the beginning, 32768. Let's run the code. Step 1, range. 30 cubed is 27,000, and 40 cubed is 64,000. 32768 is comfortably trapped right between them, which tells us our first digit is absolutely a 3. Step 2, the units digit. The number ends in an 8, and we know from our secret code that cubes ending in 8 must come from a base ending in 2. So we slap a 2 onto our 3, and there it is. The cube root of 32768 is exactly 32. And just like that, you calculated it entirely in your head.
How amazing is that? By simply observing the beautifully structured rules of math, what looked completely impossible just became a piece of cake. So, I'll leave you with this provocative thoughts. What other hidden numerical codes are just waiting to be cracked in your next math assignment? Seriously, don't just look at numbers as chores on a page. View them as thrilling little puzzles waiting for you to unlock their secrets. Thank you so much for joining me in this explainer, and happy code breaking.